looking at 1.3. 1.3, we're still going to talk about rate of change, but we're going to talk kind of comparing linear versus quadratic functions and looking at the rate of change between both of those. So first, start off with linear functions. If you guys remember linear functions for average rate of change over any length input, the average rate of change should be constant. So if it's linear. Again, if you want to write this, we talked about it a little bit on that four corners activity, but if you have a linear equation, you can normally model it by the equation y is equal to mx plus b. Again, m is our slope, or again, in this course, sometimes we call it the rate of change, the rock. You can call it the a rock, the average rate of change, to be fair. And then b, again, is our y-intercept, where it crosses on the y. Thank you. We often think of this as the slope of the line. So when we think about rate of change, you should think about it like the slope. So looking at example 1, it says the table above gives selected values of the function f of x. Explain why f of x is not a linear function. So if you look, again, normally we want to look at the inputs and see how is our inputs changing. You should see these are not equal length. Input values are going up by a different amount. I'm going up by 1, then I'm going up by 2, then I'm going up by 4. I also want to check how my y's are changing. So my y's are changing by 3, changing by 3, changing by 3. So this looks like this is constant, but the x's are not kind of at a constant rate. So I'd say not a constant rate of change. So not linear. If you really want to prove it, you can kind of show all of the different slopes or all the different rate of changes. So again, if I want to show kind of between the intervals from 1 to 2 of my x's, again, you can always use this formula, y2 minus y1 over x2 minus x1. We're going to talk about that formula a lot in this class. So especially for this first little unit. So again, I'm doing the y's, subtracting those, subtracting the x's. I get 3 over 1. If I'm going between 2 and 4, again, I'm subtracting the y's, subtracting the x's. I get 3 over 2. And then between 4 and 8, I'm going to do 13 minus 10 over 8 minus 4. Give me 3 over 4. So you should see these are all my average rate of changes, my slopes. They're all different, so they are not constant. Hopefully you can kind of see, since these were the change in x's, those actually ended up being my bottom numbers, how much my x is changing. Since my y's were always changing by 3, you could tell on the top was always that 3 number. So normally whatever our y is changing by, that'll be the number on the top because we're subtracting the y's, right? Normally whatever our x is changing by is going to be the bottom number because we're subtracting the x's. So kind of a shortcut. If you don't want to use that formula all the time, you can kind of just, what are we changing the x's by? What are we changing the y's by? Put them over each other, y over x. Those would also get you your slope. So talking about quadratics now, you should remember, hopefully, from last year in Algebra 2, we talked about quadratic functions. You could tell it's a quadratic because it's going to have a little squared for an exponent. It should be an x squared. So again, consider the quadratic function. It's a basic quadratic function. G of x is equal to x squared. Complete the table for the values of g over the consecutive equal length input value intervals below. Then complete the table for the average rate of changes for each consecutive interval of equal length input values. So if I look at here, if I want to see, again, g of x is equal to x squared. If I'm going to plug these numbers in, I can plug in a negative 3. I'll get negative 3 squared, 9. If I plug in a negative 1, I'll get negative 1 squared. I'll get me positive 1. If I plug in a 1, I get 1 squared. That's 1. If I plug in a 3, I get 3 squared and get me 9. And again, they want me to plug in a 5. So 5 squared, give me 25. If you notice, this is going down by 8. This doesn't change at all. It goes to 0. It goes up by 8. And then this goes up by, what's 25 minus 9? 16? That sound right? So those are my rates of change, my original rates of change. It's like 8, 0, 8, 16, if you can kind of see how my y's are changing. So that's kind of what's happening in a quadratic. Now they want me to find over these intervals what the average of the average rate of change is. So I'm going to take these points. I'm going to start with negative 3 and negative 1. So between negative 3 and negative 1, I'm doing 9 minus 1, the y's. And I want to subtract the x's. So be careful because this is like a negative 3 on the bottom. Again, that makes this a plus. Negative 1 plus 3. Really like a 2. 8 divided by 2 is 4. Then I'm going from negative 1 to 1. So I want to use these 1's. 1 minus 1 over 1 minus negative 1. Gets me 0 over 2, which is 0. 1 to 3, I want to use these 2's. So I'm going to do 9 minus 1 over 3 minus 1. I get 8 over 2, which is 4. And then for 5 to 3, I'm doing 25 minus 9 over 5 minus 3. Again, that gets me 16 over 2, which is 8. So again, this is my average rate of change. They are different, but you should see if I look at the change in the average rate of change, how much, or actually, sorry, it's minus 4. But if I'm going from 4 to 0, I'm going to subtract by 4. Did I mess something up? You know what I messed up? This should be a negative 4. That's why I got confused for a second. I did this backwards. It should have been 1 minus 9 on the top. I did it backwards. Should have been negative 8. Should give me negative 4. Sorry. But I kind of noticed I messed up. You should see a pattern where I'm taking these and I'm adding by 4. In the average rate of change, the average rate of change is changing by 4. You should see kind of that pattern. So in a quadratic, the average rate of change is changing at a constant rate of 4. You should kind of tell them adding by 4, adding by 4, adding by 4 on my actual rates of change. So again, normally for quadratics, the average rate of change is not going to match, but if we look at the change in the average rate of change, that's going to match. Should all be the same if it's a quadratic. It's going to go up or go down by the same amount, the actual average rate of change. So we're going to look at a couple example problems kind of on the back, but that's to kind of to introduce it a little bit so you could see. Questions on the front before I go on to the back? Let's look at a couple examples. So your homework for tonight, it's going to look like this, where they give you a bunch of tables. It's going to say selected values for various functions are given in the tables below. For each table, determine if the function could be linear, is it quadratic, or is it neither. So first thing you should do, find your rates of change. Again, see what's the change in x's. Again, here my x's are going up by 1. plus 1, plus 1, plus 1. My y's, again, to go from 0 to 1, I'm adding by 1. To go to 0, or sorry, from 1 to 4, I'm adding by 3. To go from 4 to 9, I'm adding by 5. If this first rate of change is all the same, and they're all matching, then it would be linear. But it's not. So it's, again, if this first rate of change is all matching normally, that means it's a rate of change, or it's linear. If it's not, you want to check the second rate of change. So going from 1 to 3, how would I go from 1 to 3? I have to add by 2. How would I go from 3 to 5? Add by 2. So if the second rate of change, if I find the change in the rate of change to be the same, then that's a quadratic. You should see the second rate of change, the change in the rate of change is all the same. B is going to try to trick you a little bit. They give you 1, 0, 2, 1, 5, 4, and 10, 9. The x's are not going to go up by the same amount, which makes it kind of tricky. I'm going up by 1, then I'm going to go up by 3, and then I'm going to go up by 5. If I look at the y's, it's kind of the same idea. You could tell from 0 to 1, I'm going up by 1. I'm going to 1 to 4, I'd add by 3. And I'm going to 4 to 9, I'm adding by 5. Now again, you could do all the formulas. Since they're not all the same, you kind of have to do the y2 minus y1 over x2 minus x1. But you should kind of hopefully remember that these are always going to be kind of your top numbers, and this is always kind of your bottom numbers. So you kind of know for the second one, you would get 3 over 3, and this last one, you get 5 over 5. If you want to show the work, you can kind of do it, but you get 4 minus 1 over 5 minus 2 for that one. This one would be 9 minus 4 over 10 minus 5, if I found my slopes for all of them. But again, kind of these change in x numbers are always going to be the bottom. The change in y's are always going to be kind of the top. But you should notice for all of these, my slope or my rate of change is 1. They're all the same. So since that first rate of change, is all 1, that would be linear, going up at a constant rate. Especially because these are matching kind of across. If those are matching too, that's normally a good hint that it's probably linear. And then looking at C, again, looking at my x's, to go from 1 to 3, I'm adding by 2. To go from 3 to 5, I'm adding by 2. To go from 5 to 7, adding by 2. So those are all the same. That's good. And then I want to look at my y's. To go from negative 1 to 1, I'm going to add by 2. To go from 1 to 2, I'm only adding by 1. And then from 2 to 2, I'm adding by 0. So again, this first rate of change, they're not all the same. I get 2, 1, 0. But if I think about the second rate of change, to go from 2 to 1, I'm subtracting by 1. To go from 1 to 0, subtracting by 1. So since the second rate of change is all the same, this would be quadratic. So if the first rate of change and the second rate of change, weren't matching, then it would be neither, just so you know. So could be another type of function, right? That's not linear. Could be a cubic, it could be a random polynomial, right? So it could be something else. So that's how you can kind of tell from a table. Is it linear? Is it quadratic? Look at different rates of change. Second thing that kind of goes along with this is, again, concavity. We've talked about this a little bit already. So again, concave up. To talk about this first, concavity only works with quadratics. Again, it kind of like works with parabolas, right? They look like U's if it's concave up or if it's concave down. So normally, if it's linear, it's not concave up or concave down. It's just a line, right? So in order to be a concave up or concave down, it should be a quadratic. Again, concave up looks like a happy face. Concave down looks kind of like a sad face. So again, if it's concave up, the average rate of change is going to increase across the interval. And hopefully you can kind of see, if I think about it this way, right? My graph is going to have a negative rate of change. It's decreasing. It's going down. And then right at the bottom, right at the tip, again, this is when I have a rate of change of 0, like right at the bottom of a roller coaster. You're kind of sitting there for a second. And then you would have a positive rate of change as it goes up. So again, it goes from negative, to 0 to positive. Do you guys see how that's increasing, right? My rate of change. And have a negative rate of change, it's going to 0, and then it's going to be going up. It's increasing. It's going up. If it's concave down, looks like a sad face, and again, the rate of change is going to be decreasing. I should say increase is increasing, sorry. And again, if I think about what's happening for concave down, move it like this. Again, here I start with a positive. It's going to increase. So it's positive on the left. Again, when I get to the very tip at the top, has a rate of change of 0, right, for a second at that maximum. And then it's going to go down. It's going to be negative. So it's going from positive to 0 to negative. It's getting smaller. It'll go from a positive rate of change to 0, and then it's going to turn to a negative as it goes down, if it's concave down. So my rate of change is getting smaller. It's decreasing. So they could give you a table, and they're going to ask selected values for functions k, m, and p are given in the tables below. For each function, determine if the function is either concave up, concave down, or neither. And so again, first, I want to check. I think for all of these, the x's are going to go up by the same amount. They're all going to go up by 0.01. So going up by 0.1, 0.1, 0.1 for my x's. Look at my y's. If I'm going from 4 down to 1, it's going to go down by 3. If I'm doing 1 down to -1, I'm going down by 2. And then -1 down to -2, I'm going down by 1. So you should see it's a quadratic because the second rate of change, this is going down, up by 1, up by 1, adding by 1. Technically, if you look at the sign of this, it's going to tell you it's getting bigger. It's going up by 1. So again, my rate of change is increasing. It's getting bigger. Right? It's going from -3, -2, -1, right? The next one will probably be 0. Then it's going to start turning positive. So it's getting bigger. Since it's increasing, I know it's concave up. And it has to be a quadratic, and whatever sign this tells you, if this is positive, then it's up. So that's a good way to tell. If it's negative, then it would be down. Again, all my x's here are going up by 0.1. If I look at my y's here, this is going up by 3, going up by 3, going up by 3. Again, this is my first rate of change, so this is linear. So it would be neither. Rate of change is constant, right? It's not increasing or decreasing. The rate of change is the same, stays the same. That means it's linear. It's not concave up or concave down. It just looks like a line. And then this last one, again, my x's are going up by about 0.1. Again, going from 1 to 7, I'm adding by 6. 7 to 11, I'm adding by what? 4. And then I'm adding by 2 to go from 11 to 13. So again, my first rate of change isn't matching. It's probably quadratic though, because if I look here, 6 to 4, it's going down by 2. From 4 to 2, it's going down by 2. So again, this is the rate of change is going down. It's decreasing. Going from 6 down to 4, down to 2. Again, then it's going to hit 0. Then it'll go -2, -4. It's going to get smaller. So then this is concave down. And again, you can tell because this is negative, that's how I also know. Concave down, it's decreasing.
If you do the second time, it would be going up by 2, so then it would technically be a fraction.
because the x's were different. See how these x's were the same? Then I can just look at the y's. But if the x's are different, I have to compare the x's and the y's together. Yep, and that's why I did this. I had to do all of that. Does that make sense? So your homework's pretty light tonight. It's only one side, so it's only 9 tables. So if you're looking at the first 6 are kind of like the first ones I did. Oops, did I not put it on here yet? So, in looking at your homework, 1, 2, 3, 4, 5, 6, you're going to look at the tables again, determine is it linear, is it quadratic, is it neither. So you should be looking at that. That's 1 through 6. And then for the bottom, 7, 8, and 9, you're going to see are they concave up, are they concave down, is it neither. So I don't think there's one of each. I think 2 of them are actually neither, just so you know. You don't get freaked out that you don't have one of them. Top 6 are all kind of mixed about. So you guys have the rest of the time to work. If you need help, let me know. I can walk around and help. So I'd like to think you could probably almost finish it in class.